Hi everyone, I wanted to create this quick video just to make sure we got all of the important things from the last couple of days lesson. So we started off this unit by giving some real world context to our problems. We started off with how much t-shirts cost at Target. 4 t-shirts cost $32, 7 t-shirts cost $56, and so we wanted to figure out how much would it cost to purchase 11 t-shirts, right? If I zoom in here, we can see there was a couple of different strategies that we talked about. One of the strategies that some students suggested was to figure out, well, like if I'm buying 4 of them, 4 times what number gives me the cost of 32, and some people were able to determine that that was 8. Another similar strategy is some people took the cost of the shirt, 32, and divided it by how many shirts. That would give us the price per shirt, $8. And they did this for the first and the second example and found out that they're both $8. So if they're $8, and I wanted to buy 11, 8 times 11 is 88. Another really fun strategy that I thought was pretty cool that some people came up with was utilizing the fact that here we have 4 shirts and here we have 7, so 4 plus 7 gives us 11, and therefore we can just add up like the cost of 32, cost of 56, and we ended up getting 88. Now, one other further piece that we could have done was divide by 11 on both sides and like algebraically solve for t, and that also gives us $8. So there's so many different ways and different strategies that we could have approached this problem, and they all made sense. Whatever worked for your brain was a-okay. Then we had a table with a couple of missing blank spaces, and so we had to figure out, based on the information given, like how would we fill in the table? And some people just so happened to notice that the pattern was that every x was being multiplied by 5. Like -3 times 5 is how we got -15. 2 times 5 is how there was 10. 5 times 5 is how there was 25. So they were able to guess the very last space. 10 times 5 was going to be 50. And they were able to work backwards for any other missing spot too. So what number times 5 is going to give us 40 for the second to last spot? They were like, oh, 8. 8 times 5 is going to give us 40. So that was kind of fun. Or some people kind of worked backwards and took the y's divided by the x's, right? -15, this is the y. -3 is the x. -15 divided by -3 gave 5. And we verified that for every single one. The next example that we had said to add 3 more points to the graph. The black points were already there. That would make a straight line out of the points. And so there was a couple different strategies. Most notably, though, is students started to notice that from one dot to the next, what was happening here is we were going down 2 over 1, down 2 over 1. And so we could just continue that pattern and go down 2 over 1, and we would have this point right here. Or if we wanted to go in the opposite direction, we could follow the opposite directions. Instead of going down 2 to the right 1, I could go up 2 left 1, up 2 left 1, up 2 left 1, and fill in our table. And lastly, we had our temperature problem. After 3 hours, the temperature is 18 degrees. After 7, the temperature is 2 degrees. So we had to figure out, okay, how much is the weather going, what's the temperature of the weather going to be after 1 hour? And similarly, then after 9 hours. And so a lot of different people were thinking about this similar to the t-shirt problem. But we have to recognize that it's not exactly the same. It's not like temperature per hour. That's not what we're looking for. So what I suggested and a couple students did is like maybe we started to map it out. I saw a couple students putting it on a graph, and labels were extremely important. Or as seen here, we turned it into a table. We put time on the left side and temperature on the right and started with the given facts. The first 2 given facts were like After 3 hours, the temperature is 18. So that's where we got 318 right here. And also 7 hours, the temperature is 2 is also a fact. And so we were trying to start with those pieces of information and figure out, well, what the heck is going on here? And we noticed that between 3 and 7, that was 4 hours. And from 18 degrees to 2 degrees, that was a drop of 16 degrees. Now that we have like the change in time and the change of temperature, then we can turn that into a ratio to figure out about how much is happening every hour or for each increment of time. And negative 16 divided by 4 gave us 4, right? We could see that the temperature is dropping 4 degrees per hour. Or as you can see, what we did here in the work was like 18 take away 4 would be 14. 14 take away 4 is 10. 10 take away 4 is 6. 6 take away 4 is 2. And that matched up with the facts that we had. And then we could continue that pattern to find out that at 9 hours, we'd be at negative 2 degrees and do the opposite, go backwards. Instead of subtracting 4, subtracting 4, subtracting 4, we could add 4 and figure out after 1 hour, the temperature was 26 degrees. So the main idea here is like, what do all of these problems have in common? They're 4 unique problems. They're 4 different contexts, but what the heck is going on? What is happening in all of these problems? And we were saying there was like patterns, there was context, and sometimes there was money and sometimes there wasn't. But all in all, we were using patterns to figure out what was happening. And the patterns had something that was constant. It was constantly dropping the weather by a certain number of degrees. Or it's a constant price that you have to pay for a t-shirt. Or the graph was dropping at a constant rate of down 2 to the right 1. So this introduced our next vocabulary word, or our first vocabulary word for the unit to be more direct, right? And so I want to break this up into the 2 pieces. We start with the word constant. What does that mean? And then the word rate of change. What does that mean? To be constant means it's the same every single time. Think about when we were talking about the graphs of increasing, decreasing, or constant parts of the graph. It was the same. It was the same height every single time. Now, as far as rate of changes, it's just this really fancy way, and I like to call it ROC for short, but that's the rate of change just means like, how is it changing from one thing until the next? Like, what is the amount of change that's happening from one point on the graph to the next? Or what is the amount that is changing from one t-shirt to the next if I buy 3 t-shirts versus 4? Or how is the temperature changing from 1 hour to the next? And so we can go back and think of all of these problems and identify the constant rate of change. To start here with the target problem, the constant rate of change was $8 per shirt, because we figured out that the t-shirts were going to be $8 a piece. If we go back to this table right here, the constant rate of change, remember we were multiplying by 5. That's something that's constantly, it's the same thing every single time that we're performing an operation. So here, the constant rate of change would be multiplying by 5. With our graph here, the points on the graph, what's constantly happening is we're going down 2 and then to the right 1, and we could follow that pattern, right? Down to right 1 and put another dot, down to right 1 and put another dot, down to right 1, and we were able to get that line, or do the opposite, up to left 1, up to left 1 to continue. And if we do that, we'll see that, oh, we do get all of those points right there. But the constant rate of change here is going down 2 and then right 1. Something I want to bring up and make super clear too, graphs are read from left to right. We read English from left to right. We read equations from left to right. We are going to read our graphs and interpret them from left to right. So it's really important that we say our graph is going down to right 1 and not the opposite, up to left 1. Or up 2 over 1. We have to be extremely clear that we're reading these from left to right. And lastly, as the temperature was changing, it was constantly changing at a rate of -4 degrees per hour, right? We were dropping 4 degrees every single hour. Or was it 2? Nope, it was 4. Just wanted to make sure that I wasn't misremembering that. So that's our constant rate of change, right? Something that is the same number over and over from one to the next, whether it's 1 hour to the next, one t-shirt to the next, whatever the context of the problem says. And so my question for you is, can you think of any other real world examples where there's a constant rate of change? Oftentimes we like to think of these things as something involving money if it's a set price for something. So let's say you want to go and you really like McDonald's and you want to order some French fries or a burger, right? Those have set menu prices depending on how many you would like to buy. So that is an example of constant rate of change. Now I want to move into some other examples. So let's start. It's fall time. Admission to the pumpkin patch costs $7. No, costs $4. And every pumpkin you buy is going to cost $7. Okay, so just giving us some facts again, some information that's good to know. Admission to the pumpkin patch is $4, and then every pumpkin is $7 each. It's just a flat rate, which is really nice. So ultimately, the question is, how much would we spend in total if you buy 3 pumpkins? And also, how much would you spend if you buy 6 pumpkins? And notice both of these words say in total. Both of these problems say in total. So this is going to be a slightly different problem than the t-shirts. It's similar, but it's slightly different. So if I want to start with, if I'm going to buy 3 pumpkins, right? I'm buying 3 of them at the price per pumpkin, which we said was $7. So that's going to give us $21 for 3 pumpkins. If I would like to buy 6 pumpkins, that's going to be 6 times the price per pumpkin, which is $7. 6 times 7 is going to give me 42. But that is not asking for in total. That's just straight up how much 3 pumpkins costs and how much 6 pumpkins cost. If I want to think about in total, I can't buy the pumpkins without going into the pumpkin patch, right? Admission to the pumpkin patch cost us $4 was one of our facts. So in total, I have to add my $4 to each set that I'm interested in. And so if I want to buy 3 pumpkins at this pumpkin patch, it's going to cost me a total of $25, right? It's going to cost me admission to get into the pumpkin patch and also $7 per pumpkin. So 7 plus 7 plus 7, or 3 times 7. Similarly, if I want to buy 6 pumpkins at this pumpkin patch, I have to do my admission and 6 pumpkins at the price of $7 a piece. So this is actually going to give me $46 in total for 7 pumpkins. This is slightly different than our last set of problems. Sometimes there is an admission fee or there's a cost associated going in before you even decide if you want to buy something. Another real world example might be from the cartoon Bluey. Okay, so when Bluey woke up, she had a fever of 104. After 2 hours, her fever dropped to 100. After 3 hours, her fever was gone and the temperature was back to 98 degrees. So all of this information right here is just facts. She had a fever. After 2 hours, it was 100. After 3 hours, it was gone and she had 98, a temperature of 98, which is no longer fever level. So the question that we want to answer is, what was Bluey's fever after 1 hour? And this reminds me a lot of the table or the graph even. Actually, it really reminds me of the temperature problem from the real world example too, where it might be a lot easier to determine the pattern if I have some sort of way to organize my thought process. So I like to just make tables. I think they're very clear, they're short, they're straightforward, and I like to put labels. So let's start off with the time since Bluey woke up, and also her temperature. When she woke up, time is 0, or whatever time of the day it is, but it's 0 hours has gone by. And when she woke up, her temperature was 104. After 2 hours, we know that her fever had gone down. It was 100 degrees. It had dropped. At 3 hours, it was at 98. And the question says, what was Bluey's fever after 1 hour? So when time is 1, what's her fever? So we're trying to determine the pattern, right? We went from 104 to what amount? That what amount to 100, from 100 to 98. So like we can see here, from 100 to 98, we took away 2. And notice that we have double arrows and a 4-degree difference between those two, right? This piece right here is -4, but there's 2 of them. So if it's going by equal increments, then these also are -2. And that would mean 104 minus 2 degrees would leave Bluey with a fever of 102 degrees after 1 hour. So tables are really, really useful. You don't have to. We could have definitely plotted this on a graph if you're a more visual learner, but a table is super quick, super easy, and helps our brains identify the patterns like we were talking about earlier. But this example with Bluey and this example with the pumpkin patch are different than the target problem, than the change in the weather, temperature problem. They have one additional element. So they still have the constant rate of change. That is the same, right? Like Bluey's temperature is still dropping by 2 degrees each hour. We still have the price of $7 per pumpkin. So that's still there. But I want to know, what is the additional element? So what is stand out about the pumpkin patch? Well, like that I had to pay to get in. And also with Bluey, it was the fact that we were given her temperature when she woke up, right? And so what this is, in addition to the constant rate of change, which was still prevalent within the problems, we have another piece of information that's like from the start. And what I like to call, that's what mathematicians like to call the initial value, okay? Initial value. Initial meaning the starting, value meaning amount. So, for example, the initial value for Bluey, right? For Bluey, the initial value is when she woke up and what her temperature was. That's the initial value. Another example of the initial value for the pumpkin patch was just like the price to get in or admission, right? You could, in theory, go to this pumpkin patch and not buy a single pumpkin, and it would still cost you $4 to get in. At this particular pumpkin patch, you cannot just go for free, right? That's an initial value, an initial amount of money that I have to spend for this experience, right? So, for the following problems, identify the initial value and rate of change. So we've got a handful of problems right here. Just want to make sure we get the main ideas about initial value and rate of change. So problem number 1, Denzel and his friends go bowling. The cost for the group is $15 and the shoe rentals, for the shoe rentals, and it's $4 per game. So again, I want to determine the initial value, how much we have to start, and then also the rate of change. So in this problem, how much money do we have to pay to start? We're going bowling. And regardless of how much we bowl, we have to pay $15 for the shoe rentals. So my initial value is going to be $15. If I don't play any games of bowling, I still had to get the shoes. If I play 25 games of bowling, I still had to get the shoes. If I only played one game of bowling, I still had to get the shoes, right? And then my rate of change is $4 per game. For every single game, I'm going to have to pay that $4. Second example, the gym costs $10 per month. When you first join, you have to pay a one-time initiation fee, like thanks for joining our gym, for $25. So we want to know first, what's the initial value? Regardless of working out, how much money are we going to have to pay up front before we even have our very first workout? Is it going to be 10 or is it going to be 25? Something to think about is it's like a one-time thing, right? It's a non-negotiable. So this one-time fee of $25, I'm going to have to pay that no matter what, whether I work out that day or it sometime later that week or 3 times that week, right? I'm going to have to pay that one-time fee of $25. And then for every single month, I'm going to have to pay my $10 per month. That is going to be my rate of change. Every month, I'm going to get charged $10, which is a great deal. The next problem says Roman paid $150 to join a handball club. He pays an additional $15 every time he uses one of the club's handball courts. So what we want to know is what's our initial value and what is our rate of change. So how much money does Roman have to pay just to start? He can't even play handball yet, but automatically this is what he's going to start to pay before he can even play any handball, or regardless of how many games of handball he's going to play. And this is going to be $150 to join, right? No matter what, it's kind of like joining the gym, and there's that fee that you have to go with. It's $150. And then every time he plays or every time he uses one of the courts, he's got to pay $15. So that's his rate of change. Our last example is a little tricky. We want to find the initial value and rate of change first, but let's look at the context. It says Pop-Tarts at Target cost $3 per box. Notice that this example only has one number, $3 per box. So we have to decide, is this an initial value or is this a rate of change? Is this an amount of money I have to pay to start? Is this a starting amount that I have to pay? Or is this something that is constant every single time with every single box that I buy? Is it a constant thing? And here, since it's $3 per box, that's actually my rate of change. There's nothing here that says that if I'm going to Target, I have to buy a box of Pop-Tarts, right? Or similar to the pumpkin patch example, I don't have to pay to go into Target. I can go in and I can just browse and I can decide to buy Pop-Tarts or I can not. I can buy 1 box of Pop-Tarts. I can buy 5 boxes of Pop-Tarts. It's really up to me, but there's no initial value here. Just because I go to Target does not mean I have to pay $3 to start. It says $3 per box. So one other really important thing that I kind of want to point out is our rate of change every single time has very specific words that go with it. It might say per box, every time, per month, per game. But that's going to tell you that every time or per something, that's going to be what's happening. That's the rate of change. So that is your big hint. If you're a little confused between initial value and rate of change, look for the word per, for every, things like that. And hopefully that starts to make more sense. Okay, here is a picture of Brady's savings account. And this is where we kind of were ending most of our classes. So here's a graph of Brady's savings account. Whenever I am given a graph, I like to just look at what's on the x-axis over here and what's on the y-axis over here, just so I can get some context into the problem. So x, we can see it's the month, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That makes sense. There's 12 months in the year. Perfect. The y-axis is the number of dollars in their savings account. And that makes sense because this whole problem is about how much money Brady has in his savings account. So, good to know. So, question number 1 says, find the initial value and what does this represent? Okay, remember initial value means starting amount. So, how much does Brady have in his account to start? Well, let's look at the graph. If we're starting, we're kind of at month 0 when he opens this savings account. So we're talking about right here, and we can see that he has $300 to start. He opens the account and has $300 to start. That's his initial value. Then it wants us to find the rate of change, right? And that would mean like per month, how much money is being added into his account. We started with 300 and we can see that the graph is not constant. We actually know that when our graphs are shaped like this, that means that they're increasing, right? So obviously the amount of his money in his account is going up. So the question is like, how much? With every month, how much is his account going up, right? So we started off at 300 and look at month 1. We're here at 400. At month 2, we're at 500. At month 3, we're at 600. So to kind of give you a bigger idea, I'm going to zoom in, right? At month 1, we're right here at 400. At month 2, we're right here at 500. At month 3, we're here at 600. At month 4, we're here at $700. So now that we know all of that, how much is his account going up every single month? It started at 3, then it went to 4, then to 5, then to 6, then to 7. Every single month, his account is going up by $100. So that's his rate of change, and that's how much his money is increasing from month to month. Or like, I guess I should say like how much more money he's putting in his savings account from month to month. And so now that we know that he started with 300 and it's going to keep going up $100 every single month, we can make a prediction, right? How much money will Brady have in his account after 15 months? If we look at the x-axis, the months, the biggest number it goes to is 12. So 12 to 15, that's going to be, I need 3 more months, right? And I know that every single month, I'm going to add in my $100 rate of change, right? So at my very last month of 12, I go up and I want to see how much money Brady has in his account. And oh my goodness, Brady has $1,500 in his account. So I'm going to start with $1,500, and that's at 12 months. 13 months, add another 100. 14 months, add another 100. 15 months, add another 100. Or take $1,500 plus 300, and I'll end up with how much money we have at the end, which is $1,800. Awesome. This was the main idea of what I wanted to get through on Thursday. I know I took it kind of slow here, but I wanted to make sure that it was extremely clear whether we got to this in class or if we didn't. So I hope this was helpful.